All right, this is going to be a fun little mini lecture introducing you in a very conceptual way to the idea of inertial reference frames and the two postulates of special relativity. So we've our whole study of physics thus far has really been in what we call an inertial reference frame, where Newton's first law holds true. Now, Newton's first law, remember, told us that is the inertial law, right? Objects at rest remain at rest, objects in motion remain in motion. And we are going to define an inertial reference frame as one where when we take measurements within that reference frame, or we make observations within that reference frame, so measurements, and I'm going to use these two words interchangeably because a measurement is, we can think of it as simply just a concrete observation, or one that we are looking at very carefully. So I'll probably use those a little bit interchangeably. So we take that measurement or observation as if we are at rest. In that reference frame. So what do I mean by that? Well, if you imagine that you are observing the motion of a ball. So you're observing the motion of the ball, and that ball is, you toss that ball up and you describe its motion. We know we use kinematics and forces and momentum and all those things to describe that motion. It's as if I'm on Earth observing that ball moving up and down, and I'm at rest making that observation. Okay? So I'm at rest making that observation. That's what I'm talking about. Now, it's also the case that reference frames that are moving at a constant velocity relative to my inertial reference frame are also inertial reference frames. So let me rephrase that. Reference frames moving at a constant velocity. And I'll give an example to help you through that. So a constant velocity relative to the inertial reference frame of the observer. I've already kind of defined that. Is an inertial reference frame. So a lot of feeling a little tongue twisty. Okay, so we had the example of me tossing a ball up and down and observing that ball as if I'm standing still. Similarly, if I were in a train, in a moving train, moving at a constant velocity, and I'm inside the train, moving at that constant velocity, so relative to the train, I'm at rest. Me and the train are moving together. I toss that ball up and down, and indeed it behaves as I would expect as if I was standing on Earth, at rest, tossing that ball up and down. Okay? Now, if I'm standing on Earth, and you're in that train, and you're moving at a constant velocity, and I observe you as an inertial reference frame, tossing that ball up and down, it looks a little different for me as the observer than it is to you as the person doing it inside, but you are also an inertial reference frame to me because the motion of that ball still follows classical physics, okay? And so it too is an inertial reference frame. So your moving target and your motion in the train moving at a constant velocity, relative to me standing there, you're an inertial reference frame, I'm an inertial reference frame, and we both follow classical mechanics, classical physics, okay? So those are two important things. And so the last piece is all inertial reference frames read that? Yep. All right. All inertial reference frames are the same as, or follow, all inertial reference frames follow the basic laws of physics. I want to say, at this point. All right. All the inertial reference frames follow the basic levels of physics. So, the basic laws of physics. So this idea is what we described. So I'm just going to describe it again. If I am in an inertial reference frame on Earth, the Earth is my inertial reference frame, I toss a ball straight up and down, and that ball follows the classic physics, okay? Basic laws of physics. If I'm on a train moving at a constant velocity, and I toss a ball up and down, that ball follows basic classic physics. If I'm an observer in one inertial reference frame, the stationary, let's say the stationary one, and put that in quotes in just a second, and I'm observing somebody on a train moving at a constant velocity, tossing a ball up and down, it follows the basic laws of physics. So this is what we call the relativity principle. Okay, so this is our relativity principle. All right, and that's sort of the example. Now what do we kind of take our example of the ball again. What do we notice about what's similar and what's different in that relativity principle? Well, first of all, both scenarios follow the basic laws of physics, but they don't look the same. Does that violate that? No, because they're both following the laws. But an observer in one inertial reference frame sees the path of that ball differently than an observer in the ball's reference frame. Okay, so that's important. So knowing how the observation is made is going to be critical in our assessment. Right? So the paths don't have to be the same. What's the same is that both are initial reference frames and both follow the basic laws of physics. Okay, so that's your introduction number one. And there are a couple of other key features to this relativity principle that we are going to keep track of. One is that space and time are absolute. So in this idea, space and time are absolute. Okay? What does that mean? That means things are a certain size and things take a certain amount of time, whether they're on the stationary object of Earth or whether on the moving object of the train. Now, that means that in this idea, the ball is the ball whether it's on the Earth or in the moving train. The ball's motion looks the same on the train as the ball's motion would look on Earth in terms of the time up and the time down. So those are absolute in this relativity principle, what we call actually Newtonian and Galilean reference frames. Okay? If that's true, length and time, then velocities and positions are referenced relative to the reference frame. What do we mean by that? So velocity and position go back to our train example. As an observer outside the train watches that ball going up and down, it's moving in the horizontal dimension. As an observer on the train's reference frame, and I watch that ball going up and down, it's not changing its position in the horizontal dimension. As an observer on the train, if I'm walking on the train and I'm going 2 meters per second walking, then as an observer on the train, I'm traveling 2 meters per second. If I'm an observer off the train and I am watching somebody walking 2 meters per second on a train, they're going 2 meters per second plus however fast the train's going. That's that idea of relative motion that you learned back in kinematics. So this relative motion that you've learned before is all related to this relativity principle, this type of inertial reference framework. Okay? Acceleration and Newton's second law do not change in this framework. So acceleration and Newton's second law do not change. Okay? This doesn't work if the reference frame is accelerating. All right? So if I am on a train, and I am, my train is moving at a constant velocity, and I'm walking, and I speed up while I'm walking, versus if I'm on the ground and I speed up while I'm walking, those accelerations are going to look the same. Okay, the measurement of that acceleration will be the same. The change in velocity is the same. Okay, velocity is not the same, but the change velocity is the same. Okay, so that's what we mean here. All right, and then the last principle that we really need to attend to is that no reference frame is better than another. A little bit of like karma in here. No reference frame is better than another reference frame. What do we mean by that? Well, this one's kind of fun, right? So basically this is, all right, if I'm an observer on the Earth and you're on a train, as the observer on the Earth, I see you moving, and all of your motion is dictated by classical physics, but classical physics is something that is moving. If you're an observer on the train and you look out at me, I'm actually moving relative to you. So who's to say who's moving and who's standing still? That's this point number 3. There's nothing to tell us which is the observer that's moving and which is the reference frame that's standing still. Okay? So as an inertial reference frame, you, the observer or the measurement is always standing still relative to your own reference frame. If you're observing a moving reference frame, that reference frame is standing still relative to itself. And who's to say who's, and he thinks you're moving. So who's to say who's moving? You're both, right? No reference frame is better than the other. No one is the stationary one. No one is the moving one. Okay? Which is kind of fun to wrap our head around. All right. This whole idea is the basis for Einstein's first postulate in the special theory of, theory of special relativity. All right. Oh, let me erase up this. So let's just define his first postulate. And that's all of this sort of stuff. Oh. Okay, I should erase this too. Now, we all know how cool Albert Einstein is. I'm just kind of feeling time here while I erase. We're going to talk all about his thought experiments over this little playlist of conceptual introduction. There's some math in it, but conceptual introduction to special relativity. And these thought experiments kind of get your head going, so they're super fun. To get us thinking about what happens when maybe some of these things look a little different. So far in our study of physics, we have been looking at physics as it governs these inertial reference frames. And that's been true in all of our studies, right? Momentum and energy and electromagnetic studies and all of those things. That the first postulate in the theory of special relativity is that the laws of physics have the same form in all inertial reference frames. So that's basically what we just kind of went through. Okay? So I'm not going to repeat that again in terms of kind of justifying or explaining what that means. That's really all the stuff we just talked about. So rewind if you want to kind of just wrap your head around it again. The second postulate deals specifically with light. And light's a funny beast. Okay? So Maxwell predicted that light had a specific speed. So Maxwell, all of Maxwell's equations in his work predicted that light had a specific speed kind of all the time. It didn't matter about the reference frames. It predicted that the speed of light was constant. And so there was this idea that, wait a second, that seems contradictory to this idea of inertial reference frames. So there must be a reference frame that this speed that Maxwell predicted is relative to. And if we're outside that reference frame, the speed of light actually changes. So it must be relative to something, was sort of the idea. And so there were these experiments to try to figure out what that something was in terms of what is that something's speed, so we can understand where that speed of light number comes from. Turns out nothing showed it. Okay? It was what we call the null hypothesis. The null hypothesis. The absence of it doesn't necessarily mean it doesn't exist. It just means we haven't shown it. Okay? So nothing was showing this. All right? And Einstein's second postulate actually is consistent with that idea. And it tells us that the speed of light through empty space is a definite value. So light propagates, moves. That's not how you spell propagates. Propagates. With a defined speed, a definite speed, through empty space. Here's the key now. Regardless, so independent of the source or the observer. That means if I'm holding a flashlight and running really, really fast or really, really slow towards you with my flashlight, you are going to measure the speed of that light whether I'm standing here showing that flashlight to you, or I'm running towards you shining that flashlight at you, or I'm running away from you shining that flashlight at you. You are going to measure the speed of light the same regardless of the source. Similarly, of what the source is doing, right? The source is moving, but you're not. And regardless of whether the source is moving or not, the speed of light stays the same. This is contradictory to kind of what we experience, right? We talked about the train mile, but the Doppler effect in sound, right? That mattered. What we heard depended on whether the source was moving or whether we were moving as an observer. And so regardless of whether the source moves or I move, you're standing with a flashlight and I run towards you or run away from you, the speed of light is always measured the same. So Einstein postulated that this is just, it's a constant in a vacuum, right? In empty space. And that actually is consistent with that experiment, the null effect, right? Because we didn't say anything differently. And it's consistent with Maxwell's predictions. So this is our second situation, okay? And it's hard to reconcile, as we've said, in terms of kind of other things that we've done. So what is that, okay? Well, the speed of light, we're gonna get to some of those fun thought experiments. We define the speed of light as c, and it's 3.0 times 10 to the 9th meters per second. So it's super fast. But this was what was predicted with Maxwell's equations. Okay. Somehow that number's shaking me. Let me confirm it. Find it in my confirmation, because for some reason I'm feeling a little funny about that number right now. I want to make sure I don't go through this whole lecture. Well, how do you do? We're going to go with it because I can't find it in my notes. 10 to the 8th, 10 to the 9th. It's worth looking up because, again, I am, the more I try to think of it, of course, the more nervous I get that that's not the right number. As I'm sitting here. 1, 2, 3, 4, 5, 6, 7, 8. See, I'm glad I looked it up. What kind of physicist doesn't know that number? Double check it. 1, 2, 3, 4, 5, 6, 7, 8. 8. Boop. There we go. Glad I looked. Awesome. We're going to do some fun thought experiments. That's what all of this relates to. And a couple of mathematical experiments. It's going to be a good ride. Good job.